Well, welcome to our lesson on logarithmic functions and their graphs. This is section 3.3 in your textbook if you care to follow along. And our learning targets for this lesson are to be able to convert between logarithmic and exponential notations, to evaluate logarithmic and exponential functions, and to apply special properties of logarithms to solve problems, and lastly to determine graph transformations of logarithms. So let's go ahead and get started. One of the primary tasks or skills that you will need to know how to do is to convert between the two different notations, between logarithmic and exponential notation. And logarithmic functions turn out to be inverses of exponential functions. So they help us to solve exponential equations in the same way that multiplication and division are used to solve equations. They undo each other. The same is true for logarithms and exponents. So the relationship between logarithms and exponential functions are given by this relationship. If we have the log of y to the base b equal to some number x, then to write that exponentially would be b to the x power equals y. So we call little letter b here is the base of the logarithm. It is also the base in the exponential notation. X is considered the exponent, and then y is the output. So we already know from previous chapters about the domain and the range of exponential functions. X could be any real number. It could be positive, negative, it could be a fraction, it could be a decimal. It doesn't matter, it could be anything. But we always get an output that is greater than 0. We never get any negative values for y. Well, this also holds true for logarithms. They have the exact same properties. So the domain is all reals, and the range is only the positive real numbers. So let's go ahead and use this relationship that we've listed here to go ahead and evaluate these logarithms without using a calculator. So we want to write this in exponential notation. So our base is 5, and we're going to raise that to some value that we will call x. So we're going to have 5 to the x is equal to 125. Well, how can we write 125 with the same base? Our goal is to get our bases to be the same number, because if our base is the same, then the exponents have to be the same as well. So 125 is a power of 5. It's 5 to the third power. So x must be 3. Over on letter B, we can write 7 to the x equals 1. Well, how do we get a 1 out of a 7? What power of 7 gives us a 1? Well, that has to be a 0. Anything to the 0 power is 1, with the exception of 0. 0 to the 0 is undefined. Letter C, we have 1/3 to the x is equal to 81. Well, 1/3 is really 3 to the negative 1 power. That's really the reciprocal of 3. And 81 is also a power of 3, so 3 is going to be the base we're looking for. Well, this is really 3 to the minus 1 raised to the x, and when we have a power to a power, we multiply. So this is 3 to the minus x power is equal to 3 to the fourth power. If you don't know these powers of your very small numbers, 2, 3, 4, make sure you get familiar with those and recognize that 3 to the fourth power is 81, or you're going to struggle with these a little bit. So once we have our bases equal, we can set the exponents equal. So negative x is 4, so x must be negative 4. Letter D, we have 8 to the x power equals the square root of 2. Well, to write 2 as an exponent, that's really 2 to the 1/2 power. And 8 is also a power of 2. That's 2 to the third power. So we get 2 to the 3x equals 2 to the 1/2. Now we can set our exponents equal and solve for x, and we get 1/6. Here are 4 common properties that we will be using with logarithms. And the first property says that if you have the log of 1 to any base, that's equal to 0. And that's true because the base to the 0 power equals 1. If we have the log of any number and the base matches that number, we end up with 1. If we have the log of a number raised to a power y, that the base drops out and the log drops out, and you end up with just whatever the exponent is. Because if you write that exponentially, b to the y equals b to the y. And then similarly in property number 4, if we have an exponential expression where b is our base and we raise it to a logarithm with the same base, those all drop out and you're just left with whatever you were taking the log of. It's equal to x. So we're going to use those properties in just a minute. And I wanted to talk to you about, there are two special kinds of logarithms that your calculator does. One of them, and you're probably already familiar with this, one of them is called the common log. Its base is 10 and it's written log of x, the log of x. The other one is called the natural log. It has a base of e. Remember, e is just a constant number named after Euler, and its value is 2.718 approximately. And we write that log as ln, the natural log of x. So those are the two buttons that you'll see on your calculator. One of them is log and the other one is ln, and they're along the left-hand side of your calculator. So let's go ahead and use some of these properties to evaluate these expressions without using our calculator. Letter A, we have the log of 6 to the third power to the base 6. Well, since our bases match, we just are left with the exponent, which is 3, and that is property 3. Letter B, the log of 10 to the fifth power. Well, log, common log, has a base of 10, so again, our base drops out and we're just left with 5. Letter C, we're taking the base e and raising it to the natural log of 5. Well, the natural log also has a base of e, so those cancel and we're left with 5. That's property 4. Letter D, this one takes just a little bit of work. The natural log of 1 over e is the same as the natural log of e to the minus 1 power. This fraction, 1 over e, is the same as e to the negative 1. So again, our base matches our base of the logarithm, so we're just left with the exponent negative 1, and that was property number 3. And then the log of the fourth root of 10, well, we can write 10, the fourth root of 10 is 10 to the 1/4 power. So again, the bases match, and we're left with only the exponent, property 3. In this slide, I wanted to give you a graphical representation visually so you can kind of see how logarithms relate to their exponential inverses. So in the first graph, this is the log of any base, b, in general, and it is symmetric about the line y equal x. All of these are symmetric about the line y equal x. In the middle graph, you see the common log with its base 10 exponential equation. And on the right-hand side, you see the natural log with its base e exponential expression. So the one thing to notice, if you compare the two graphs, the middle and the right-hand one, a base 10, it's a bigger base, so our slope is going to be a little steeper. You'll notice that in the exponentials. And the opposite will be true then for the logarithmic function. So one of the cool things about logarithms, all the stuff that we learned about graph transformations, those rules also hold true for logarithmic functions. So let's go ahead and see if we can describe how these functions differ from their parent functions, whether it's the common or natural log. In letter A, this one, we're subtracting 3. This is inside the function. So again, since we are inside the function, that's going to be a horizontal translation, and it's going to be to the right 3. Again, in letter B, it's inside the function. We got to do a little work on this one. If we switch the x and the 4, it's a negative x plus 4. And remember, we always need that x to be positive to get the correct direction. So we need to factor out that negative. So that tells us it's going to be translated to the right 4 units. But this negative, since it's inside the function, also represents a reflection across the y-axis. And then letter C, we have 2 being multiplied outside the function. So this one is a vertical stretch by 2. And in letter D, we have a 2 outside the function being added. So that tells us we're translating that one up 2 units. All right, so here's a specific application of logarithms. Sound intensity follows a logarithmic expression pattern, and sound intensity is measured in what we call a decibel. You've probably heard of that before. It's named after Alexander Graham Bell, And the expression or the function that it follows, beta, which represents the number of decibels, is equal to 10 times the 10 times the log, the common log, of the sound intensity divided by the I sub 0, which is called the threshold of human hearing, and that is a constant value. And that threshold is equal to 10 to the minus 12 power. It's the smallest or the quietest sound that a human ear could hear. So I've listed a table here. I've given you a table with several different sound intensity values that have been measured and recorded for us. And you would use this when you have a problem such as this. Say you wanted to know how loud a train is inside a subway tunnel in terms of the number of decibels. So you would use the equation that was given above, 10 times the log of I over I sub 0, and then just substitute in 10 to the minus 2 for the value I. So that says that the decibels are equal to 10 times the log of 10 to the minus 2 divided by 10 to the minus 12. Well, remember our exponent rules. If you're not familiar, if you don't remember the exponent rules, please consult the front cover of your textbook. There's an extensive list of both exponents and radicals, all the different rules for working with those. You should have learned those in Algebra 2. If you have questions on those, ask me in class. I'd be happy to help you. So 10 to the minus 2, remember when we're dividing and the bases are the same, we subtract the exponent. So we're going to have 10 times the log of 10 to the 10th, because we have negative 2 minus a minus 12, which is negative 2 plus 12, which is 10. And remember when our base and our log base are the same, they drop out. So we're left with just the exponent 10. So we have 10 times 10, which is 100 dB. All right, the last slide here is a lesson check for you to work on. You should be able to do all of these without a calculator, 1 through 8, and then describe the graph transformations in 9 through 11, and bring those answers to class. See you next time.